Hello. In this podcast, we're going to talk about the conservation of energy, a very important concept in mechanics. But first, let's review what we know about energy. It's a substance-like quantity that can cause change, make objects move, make things stop. It's needed to do work. And while we can think of it as a substance, it does not have mass or volume. Energy is stored in objects using one or more storage mechanisms. It flows from one storage mechanism to another storage mechanism within the same object, and it can also flow from one object to another object. The 6 storage mechanisms, which we covered in a previous podcast, are ways in which energy is stored in objects. They are gravitational potential energy, elastic potential energy, chemical energy, kinetic energy, thermal energy, and dissipated energy. Lastly, in our review, energy flows between objects or flows between mechanisms within the same object by way of transfer mechanisms. So the 3 transfer mechanisms are working, heating, and radiating, also sometimes known just as work, heat, and radiation. So let's take a look at the law of conservation of energy. Energy can neither be created nor destroyed during physical and chemical changes. Now, one thing I want to mention here, nuclear changes are the exception to this law and the law of conservation of matter. During nuclear changes, mass is changed into energy and vice versa. But in mechanics, we're going to be talking about physical changes. When investigating and analyzing energy changes, it is essential to clearly define the system you are investigating. A system is simply the environment you are studying. It could be a single object or a group of objects. In this picture, the system could be just the coiled spring or the spring in the car. You need to define your system before you can analyze energy's effects. Since energy can neither be created nor destroyed, the change in the system's total stored energy is equal to the energy transferred into or out of the system. So for example, if we have changes in any of these 6 storage mechanisms within an object or a system, then those changes have to be the result of some energy coming into or leaving the system, either by work, heat, or radiation. So this leads us with a simple equation. The change in kinetic energy plus the change in thermal energy plus the change in dissipated energy plus the change in gravitational potential energy plus the change in elastic potential energy plus the change in chemical potential energy is equal to the energy flowing into or out of the system by work, heat, and radiation. Just a note here, energy transferred out of a system, we give the negative sign, and energy transferred into the system is considered positive. Although I do want to point out, energy is a scalar quantity. It is not a vector quantity. Let's move on. The total energy is the sum of all the object's energy. So you take up the energy stored in all 6 of these mechanisms, and that is equal to the total energy, often called the internal energy of an object. And it is represented by the symbol capital U. Let's do a learning check. Pause your video and see if you can answer these 4 questions. We'll be right back with the answers. Okay, let's see how you did. Let's learn 2 ways we can record our energy observations. These are both qualitative and quantitatively. Qualitatively, we can use pie charts to show the relative amount of energy stored in each of the 6 storage mechanisms. The larger the slice of the pie, the more energy that's in that specific mechanism. Quantitatively, we can use bar charts, or what I call column charts. And here we just use generic units to represent how much energy is stored in each mechanism. So for example, in this column chart or bar chart, we have 1, 2, 3, 4, 5 units stored in the gravitational potential energy mechanism. Then 1 unit of energy flowed into the system through the transfer mechanism of work, and after that energy flowed in, we wound up with a total of 6 units of energy in the gravitational potential energy mechanism of our object. This chart is also an example of how the law of conservation of energy works. The final gravitational potential energy has to be equal to the initial gravitational potential energy plus the amount of energy that flowed into or out of the system via a transfer mechanism. In this case, work was the transfer mechanism. Now, for mechanics, we can make some simplifications. Chemical potential energy and thermal energy are storage mechanisms that usually do not change. So that means we don't have to worry about showing them. However, sometimes the chemical potential energy will change. Typically, this is when we have an engine involved and the potential energy in the gasoline is being transferred into some other storage mechanism, or it could be a person pushing something or throwing something, and there they're using the chemical energy stored in their bodies. But often we don't have to worry about chemical potential energy. Dissipated energy is zero in ideal frictionless conditions. So if you have friction, you're going to have energy flowing into the dissipated energy mechanism. But if there's no friction, you're not going to have any dissipated energy. Heating and radiating are not used to transfer energy. Only work is used. And finally, instead of looking at total internal energy, we look at mechanical energy, and it's the sum of an object's energy that is stored in the kinetic, gravitational, and elastic storage mechanisms. Based on these simplifications, we can take the previous equations for energy and rewrite them like this. Instead of the total energy equation, we can say that the mechanical energy of an object is equal to its kinetic energy plus its gravitational potential energy plus its elastic potential energy. We have two simplified equations that we can use to analyze changes in energy. The first one we'll use when there's no friction, and that tells us that the change in the mechanical energy of an object is equal to the energy that flows into or out of the system by the work transfer mechanism. The second one is when we have friction, and there the change in mechanical energy for an object is equal to the amount of energy that flowed into the system or into the object by the work transfer mechanism minus the amount of energy that flowed into the dissipated bucket. Remember, friction causes unrecoverable energy, and that's represented by the energy in the dissipated mechanism increasing. So when we have friction, not all of the energy transferred goes into the mechanical energy of the object. Some of it goes into the dissipated mechanism, and remember, that energy is not lost, but it is unrecoverable, which means it can't be used for anything useful. Let's do a learning check. Pause the video and see if you can answer these two questions. I'll be right back with the answers. Okay, let's see how you did. First question, if an object's kinetic energy increases while the energy stored in the gravitational and elastic mechanisms remains constant, was energy transferred into or out of the object? Well, energy was transferred into the system because the object's total mechanical energy increased. Now, let's do a bonus question. What was the energy transfer mechanism? Well, it was the working, also known as work transfer mechanism. Let's move on to the second question. If a rubber band's elastic potential energy decreases while energy stored in the kinetic and gravitational mechanisms remains constant, was energy transferred into or out of the rubber band? Energy was transferred out of the rubber band because the object's total mechanical energy decreased. The bonus question once again is, what was the energy transfer mechanism? And once again, it was the working transfer mechanism, also known as work. Well, this wraps up our podcast on conservation of energy. I hope you found this information useful, and have a good day.